Okay, the time it takes for an overcurrent protected device to open is plotted on what is called the time current characteristic curve. It's a pretty fancy name, and
Fancy curve.
let me just explain what it is, and then we can get into some details. Ready for this? Brian, maybe we could put like 1,000 amps over here. So this is amps, okay? This line right here is amps, okay? And then over here on the left-hand side, so this is current right here. And then this up here is time. So you can see it starts at 5 seconds, and of course some value would be significantly less than 5. And we're talking about a big broad stroke here. So now, here is a 20 amp breaker. And if I took 20 amps, and maybe we can put 20 amps here, and if I went from 20 amps and I go up, it should just miss this red line here, which means that on time-wise, you should be able to put 20 amps on a 20 amp breaker continuously.
Definitely.
Now, if we go to 40 amps, well, 40 amps, you go up. Well, the red line indicates the minimum time it's going to take to unlatch that circuit breaker, because you taught us about latching. So 40 amps goes over here. It says, well, you know what? It could, because of the bimetal, it could unlatch in about 25 seconds, but it might not. And then you go up a little higher on this 40 amps on a 20 amp breaker. Well, it might take 150 seconds, where the thing comes out to be about, is that 2.5 minutes? 150?
Yep. 2.5.
Yep, 2.5 minutes.
So 40 amps. Remember I talked about take a coil of 12 gauge wire. If you go to chapter 9, table 8 in the back of the code book, it says it's rated, has a resistance value per M feet of 2 ohms per M feet. 500 feet of 12 gauge wire therefore has a resistance of 1 ohm. I put in 120 volts, and because there was some impedance because of inductance, that resulted in the current to be no more than 40 amperes. So when you hook that up, initially, you'll hear the wire vibrating, making all this noise, and you're freaking out. And you might even put an amp meter on, but get it far enough away from the coil of wire, because the electromagnetic field could affect an amp meter reading. And all of a sudden it's drawing 40 amps, and it didn't trip the breaker. It takes about 40, my experience, I guess different breakers, different time current characteristic curves, might take 2.5 minutes. Now what happens? It takes 2.5 minutes to trip it the very first time, but then the breaker is now hot. And if you, okay, let me show you that again, guys or ladies. And then when you reset it and you try to do that experiment again the second time, the breaker, Tom, already has heat in that first experiment. And then when you try to turn back on again, well, it's not going to go, let's say, 2.5 minutes. Oh, man, I tripped in like 45 seconds. And then you say, well, let me show you guys again. And you put it back on again. Well, we've already generated heat in the breaker itself. So that's why it would take less time each time. Of course, you would never turn breakers on in the event of overload conditions like that. But I wanted you to understand that Tom was explaining how that bimetal heat is functioned. And so, Tom, a circuit breaker that's rated 100 amps is rated 100 amps at a certain ambient temperature under a certain condition. And if we put it on the west side of the house, let's say for an air conditioner or whatever the equipment might be, all of a sudden that breaker might be tripping. Well, because it's not a 100 amp breaker anymore, because the heat that from the ambient temperature elevated the heat in the breaker, and so now it changed the calibration of that breaker. Yeah. So assuming that it's installed in the ambient temperature that is calculated at, assuming that we have the time current characteristic curves, we can say a 40 amp breaker going up could minimum tripping time would be about 25 seconds. The maximum unlatching time would be about 2.5 minutes, and that's what it looks like. So that's why 40 amps on a 20 amp breaker is not going to be tripping instantaneously, because it's a time, it's heat, it's a bimetal bending it. Now, let's go with 100 amps. Well, if you had 100 amps, well, you go up and over, minimum, maybe half, 5 seconds. And it could take, the unlatching time is between 5 seconds, and maybe it goes up to 20 seconds. And this one we were talking about the inverse time characteristics. This applies to fuses. If we had a time current curve, we could have done the same thing here and shown this as a fuse. Now, what's the next step? If you go all the way over here to the right, and let's assume that this number is significantly greater So maybe 500 amps, right? We could have five. Well, if you put 500 amps on a 20 amp breaker, this line right down here, which is not quite perfect, but this line down here is that it's going to trip. Maybe we can put some value down here, Brian, on the left-hand side, of some very, very low amount of time. And Tom, at instantaneous, if we're going to put a number here, what would be a reasonable number we can hear in seconds?
0.01.
0.01.
0.01. Okay, so if you had 500 amps, but Tom, correct me if I'm wrong. When we go to 500 amps, this is not an overload condition. This is a short circuit condition, and that was where the armature inside the breaker that was latched, it's an electromagnetic field. Now that field is doing what? It's unlatching. And Brian, you said, well, circuit breakers takes time because it's a mechanical device. So we have this high electromagnetic field. That high electromagnetic field is now going to unlatch it, and then it takes some physical time for it to actually open up the contacts. So watch what we're talking about here. If you have an overload condition, and I probably should shade it on the left side, well, it doesn't matter. Overload condition, it's going to take time. In order to get down to the 0.01 time, which is 10/100ths of a second, remember the decimals, the number of decimal places we talked about in math? That you're going to have to get to some value that's going to go to, correct me if I'm wrong, Tom, that's going to go to the instantaneous trip range. Now, Tom, the instantaneous trip range, and I'm going to say a statement, and you can say, Mike, that's okay. It's okay because you've been painting with a big brush. But is it about 10 times the rating of the breaker? In other words, if I have a 20 amp breaker, if I get about 200 amps, that I then get into the electromagnetic field part that opens it? And about how many times will it take of the current of the rating of the breaker to get me to instantaneous?
So UL did a study, because this has been a question.
Oh, okay, good.
It's been a question. The important thing to remember about the instantaneous, it's not governed by any standards.
Right.
I'm not required to put an instantaneous in a circuit breaker at all by any standard. So if I do add one, it's up to me on what value I want to put it on. Now, you can go to a lot of literature and find the 10-time. A lot of people use the 10-time number, and a lot of times they're wrong, right? Because you think about a 20 amp breaker. Okay, UL did a study, and they just basically went to your standard big boxes, grabbed a bunch of breakers off the shelf,
This is cool.
and they took them back into a lab, and they ran a test. And they determined what they were, and they said their initial testing suggested that 99% of all...
Hold on one second. You say, Mike, there is no standard, and people can decide, and you don't have to have an instantaneous trip.
Right.
But if you want to, you guys decide whatever you want to do, and everybody's doing their own thing, and somebody said, hey, I wonder what that would be, and they're like, you know what, I don't know. We'll go buy a bunch of breakers, we're going to test them, and we're going to find out what it
Right,
is.
exactly.
Well, okay.
Exactly.
Okay,
Yep.
so I'm with you there. Go ahead.
So they said that 99% of all circuit breakers would magnetically trip, which is your instantaneous, at or below 300 amps for a 15 amp breaker. Now, is 300 amps for a 1500 amp breaker anywhere near 10 times?
No.
And these are standard residential molded case circuit breakers. And 350 amps for a 20 amp circuit breaker. And then they did additional testing. And it says 1 year later, they negated those findings. And what they found was that the instantaneouses could be as high as 400 to 450 amps on those circuit breakers. And I'll tell you why.
Oh, yeah, I'm curious.
The reason we do that in many cases is because of what you said earlier. You said about the temperature. And the other thing you didn't mention is elevation,
Yeah.
which I know you know all about.
Oh,
right?
yeah.
So when you have some of these loads may draw a significant amount of current. You have a lot of current loads will have inrush currents and all that good stuff. So we specifically will increase that instantaneous so that we don't get the phone calls that your breaker tripped. So we bump it up. Can I do that? I can do that at will. I don't have to notify UL. I don't have to notify anybody because I'm not even required to have an instantaneous. So the big misconception is all you need to worry about is 10 times. And that's just not a fact. And it's not coming from me. This is a UL study. And the reason I know a lot about this is because we did this research for activities that were going into the code on Code Making Panel 2. Right? And UL did it as an independent study to verify that the manufacturer who's, because I'll sit at the table and I'll say, somebody will present and they'll say, well, here it is. This is what we're suggesting. I'll say, well, that's not true. The instantaneous isn't 10 times. And they go, oh yes, that's what I was taught. I was an apprentice and I did this and that's what I was taught all these years. And you go, no, it's not true. And then I tell them what the facts are and then they say, well, I don't believe you. So then UL did a study and they said, it's true.
So that means that I can't say 10 times in my book. I can say some value, right? Because you said, hey, well, the study showed at 300 amperes. Well, I think that's 20 times. Well,
20 times.
Yeah, take it up to 20 times. Yeah, it's going to clear instantaneous. But what below that? Okay, Brian, you were going to say something?
Well, Tom just said something that I just want him to clarify a little bit. So instantaneous trip, you mentioned temperature and elevation.
Yeah.
Okay, so just from the world that I know that I dealt with as an electrician in the field, temperature typically impacted my overload, right? I got a panel on the west side of the house. It's 150 degrees, so I usually equate temperature with overload.
Right.
But you equated temperature with instantaneous, which is the magnetic thing. So
think about the
what is
construction.
that?
Think about the construction of that breaker.
Okay.
Okay, and remember that the overload and the instantaneous are all a part of that same mechanism.
Right.
And it's the same latch inside of the same slot. So if I am impacting the overload because I'm moving that mechanism,
Right.
it's going to impact instantaneous too.
Okay.
But it depends on the design
breaker.
of the breaker.
I understand, but I just
That's
wanted to
the key.
clarify that a
No,
little
you're
bit.
right. You're absolutely right.
Okay.
Now, if I have an electronic trip units, see, that's the advantage that you have in those heavy commercial and industrials. When you have electronics and brains, you can make adjustments for things like that. But when you're dealing with a very mechanical device,
Okay.
which impacts fuses as well.
I don't understand. What is altitude? I mean, I live at 7,000 feet with Eric. We both live at 7,000. I go, snow skiing or I go mountain biking at 10, 12,000 feet. What does it have to do with the circuit?
How many times did you drop it?
Gosh.
I had to do
Gosh.
that.
Okay.
I'm never living this down.
Okay. All right.
No, but elevation does, and I can't.
Okay.
It's like it's a density. And,
Okay.
Air density,
Right.
yeah.
Okay.
Yeah.
All right, we'll move
Heat
on.
radiation.
All right, back to
Exactly.
our time current characteristic curves. Some value that's pretty high in relationship to the rating of the protection device will take us into the instantaneous trip setting. And the time current characteristic curve is going to be different for every different type of manufacturer, different breakers. And so let's just stop right there. That's what this chart is about. Now, let's see if it's right. The time it takes for an overcurrent protection device to open is a function of the current of the overload, above the ampere rating of the device. As the overload increases, the time it takes for the thermal trip element to open decreases. I think we've established that, right? That was where we said, okay, well, at 40 amperes on a 20 amp breaker, 40 amperes is going to be between basically a half of a minute to 2.5 minutes. But if you brought it up to 100 amps, it could be between 5 seconds, minimum latching, unlatching, and maybe 20 seconds. Just big stroke, okay? I got that, and we got that taken care of. To clear short circuit, the short circuit current must rise to a level that is at least 10 times, which I have to get it out of my book because you say, well, people have it in their books. They're teaching people things like that. Okay. It has to be some high value. Once it reaches the instantaneous range, so here's an example, and we probably need to maybe not put 200 amps here because we don't know if it's going to be 200 amps. But there's a little slightly different. So here, the blue here is the thermal because it's not going to trip instantaneous. And then showing the yellow over here, well, that's when you get into the instantaneous, and we don't know how many times it is to get to instantaneous, but when it does get to instantaneous, then it can trip at 0.01 of a second. We're going to go down here. There. All right, I see that. Clearing ground faults. Well, a ground fault is the same thing as a short circuit, and we mentioned in the graphic here 10 times, which we can't say. So we're going to go here, and for a ground fault value, if you got to the instantaneous, it's going to trip it very, very quickly. And then, of course, thermal, longer time. All right? Low impedance ground fault current path. To remove dangerous touch voltage on metal parts produced by a ground fault, the fault current path must have sufficiently low impedance, not resistance, because we're alternating current circuits, to allow the fault current to quickly rise to open the protected device. Let me just kind of show a picture here. So, okay, if there's a fault condition, see, when you have a ground fault, which is defined by the National Electrical Code, and we're having a phase wire touching metal parts that we've seen previously a couple of slides before, well, then the metal parts become energized. Now, the metal parts become energized until they open under a ground fault condition. And Tom, we don't know what the ground fault value is going to be under any set of circumstances. The wire could just be brushing against it. It could be bolted against it. When you have a ground fault condition, there could be some arcing that could take place. That creates impedance. The arcing also adds some impedance, meaning there's higher kind of resistance with AC. And depending upon the impedance of that ground fault determines the current of the fault. So if we know what the current in the fault is, and then we find out protected devices, time current characteristics are different for all kinds of things. And I would have said, but I did, well, if you can get that ground fault current to be 10 times, you're going to go into instantaneous. Well, let's not say 10 times. If we can get the ground fault current to get to the instantaneous, then we're going to be clearing instantaneous, which would be beautiful. But the code does not tell us how fast we have to clear that fault. It doesn't tell us. Right. So now when you get into the impedance of the path determines the value of the fault. The value of the fault determines how long it takes for the protected device to open. The time it takes for the protected device opens tells you, well, how long is everything going to remain energized. So now let's look at the graphic here. So the code works this way. You have a transformer, simple basic transformer. Electrons leave the source. They go out to some load. There is a ground fault that, let's try this again. We have a transformer. Electrons leave the source, go through a protected device. That's protecting against short circuit, ground fault, and overload. And there's a ground fault. Fault current travels on a wire that's called the equipment grounding conductor. Just know that it's a wire going back over to the source, right? So all these little components come together. So electrons leave the source. There's a ground fault. Ground fault current does not go to ground. It returns back to the source. Now this path right here, that's the path that Tom's talking about. The impedance of that circuit determines the fault value or the current value of the circuit. If we knew what the resistance or the impedance of the wire was, and if we knew what the impedance of the fault was that we don't know, and if we knew what the impedance of the return path back to the source was, let's just assume it was 100 feet of 12 gauge wire in Chapter 9, Table 8, and the code book tells you it's 2 ohms per 1,000 feet, which means it's 0.2 ohms per 100 feet. Let's say we're running a 12 gauge wire back over to the source, and it's 100 feet. Well, if it's 2 ohms per 1,000 feet, well, 100 feet is 0.2, so we know we have fault current going out of 0.2 ohms, fault current returning back to the source at 0.2 ohms, and using Ohm's law, I is equal to E. Oh, Mario, we need to change this R
to Z.
We have to change it to Z because we're an alternating current. So R is equal to E over Z, and so therefore it's in ohms. 120 divided by 0.4 is 300 amps. Now this is 300 amps, and let's say this is a 20 amp breaker. And Tom, you said, hey, 99.99% of the time it'll probably get it instantaneous. Well, guess what happens if we do that? We take that circuit, we have a fault return path, the low enough impedance to drive that fault current up so high that we can get it instantaneous. But that all is driven based upon the amount of available fault that can even get there in the first place. So we didn't talk about short circuit currents as it goes down the line here. So assuming everything was perfect, and assuming you could get this, assuming we ignore the arcing fault that takes place here, everything else like that, if we get instantaneous, but we don't know what it's going to be. But the important part is this. We do need to make sure that there's a fault return path to go back.
Right.
Right here. Take a look at this. This is the code. It says, listen, you have to size this wire. You have to make these connections. You have to do them in certain ways. We have to do the best that we possibly can to have the low impedance fault return path to facilitate the opening of the overcurrent device. Now, there are two parts or some code sections in here, Mario. There's a section, and I'll just tell you because I don't want you to have to scramble to know. 250.4A5 in the National Electric Code. I think it's 5. I think it might be 4. The one that I'm looking for, Mario, about facilitating the opening of the protection device, and there's a definition in Article 100. It's talking about the effective ground fault current path. So now this is another name that you don't have to worry about right now. Just want to kind of put it in context. It's a word, in name only. I mean, it means something. See this green path right here? From here all the way back here, the National Electric Code calls it an effective ground fault current path, just to give it a name. But it represents components. This is, don't have to worry about this. We're going to be covering this when we get into bonding and grounding. That's a supply side, that's a system bonding jumper, supply side bonding jumper, equipment grounding conductor. When you bring all those components together, it gives you an effective ground fault current path for the purposes of facilitating the opening of the protection device. So Mario, what rule talks about facilitating the overcurrenting?
That would be 250.4 A5.
It was A5.
It was A5.
Okay. And so now, Tom, we did the best we could. We don't know how long it's going to take. We don't know what the available fault's going to be, and we don't know how long it's going to clear. Right, guys? It's just,
But in reality, I mean, you're talking about protecting that ground conductor and whatnot, right?
no, I'm just talking about clearing the fault.
Clearing the
Clearing
fault. Okay, yeah.
So we do the best we can. We go to the
Open
code
the
book. We do the best we can.
Exactly.
But there is no value that says you have to size it, you have to install it, so that it goes into, so that the fault will be at the instantaneous trip setting. We're just following the code. And I'm going to move on unless somebody else wants to talk about it.
Yeah, I need to make a comment. I think on that graphic, you had told Mario maybe to change that R to a Z. I think you should leave it an R. And the reason I think you should leave it an R is because if you put a Z in there, then you probably ought to actually use the Z values. And this is a great graphic for illustrative purposes. So I think you should leave it the R.
You're right. Just opposition. And I'm honestly kind of
Right.
shocked that you said that, but I'm going to go with it.